For this lecture, we'll be discussing approximation methods in quantum mechanics. So it turns out that for problems that are a little bit more complicated than the ones we've been solving so far, systems such as multi-electron atoms, starting from helium, going on to lithium, so on, have three or more particles, and it turns out that if you have three or more interacting but independent particles, the Schrodinger equation doesn't have an exact closed form solution. We can enumerate all the forces and the associated potentials, but what we can't do is find a wave function that is a wave function solution. There's no closed form wave function solution. And it turns out that this problem, you might be tempted to conclude, well, quantum mechanics is complicated, and so that's why you can't solve these three-body problems. But it turns out this is a problem even with classical Newtonian physics. You need to use approximation methods if you're dealing with orbits of multiple interacting bodies, such as the Earth, Sun, Moon system, or if you try to put more than one planet in orbit around the Sun. And so to solve these problems in the case of Newton's equations and in the case of quantum mechanics, Schrodinger equation, we need to use approximation methods. But these approximation methods, it doesn't mean that the results aren't accurate. It just means that you often have to get the result by some sort of successive approximations, multiple calculations, and we'll talk about, and that leads to some trade-offs that we'll talk about later. So Laplace, in dealing with Newton's equations or Lagrange's equations, the Lagrange reformulation, developed this perturbation theory for solving the problem of complex planetary orbits, including three or more bodies. And you can solve essentially to arbitrary precision, and there's a trade-off in terms of you can achieve more accuracy, but that's going to require more iterations of the perturbation theory to get a more accurate result. So there's a trade-off between accuracy and computational effort. There's another trade-off that we'll talk about later. So in quantum mechanics, and of course there are some other approximation methods for Newton's equations as well, in addition to Laplace's theory. There are, so let's move to quantum mechanical approximation methods. Those include perturbation theory, very similar in some ways to Laplace's, share some similarities to Laplace's approach in classical mechanics. There's another, now that said, we're going to skip perturbation theory for now. It's covered in the textbook chapter, and it sort of makes sense to put these various approximation methods together in one chapter. However, we won't really be applying perturbation theory until we move to some other problems later in the course. And so I'm going to skip that for now, or postpone it for now. And we'll mostly talk about the variational method, which will get us through the multi-electron atom and the H2 plus molecule ion. Okay, so so one might wonder, why do we want to cover quantum mechanical approximation methods? Because you can just let a computer solve things for you. using computational quantum chemistry software. Um, so we'll be learning about more basic methods that are less accurate, perhaps, in most cases, than sort of state-of-the-art computational software. However, these basic methods will help explain essentially how this software works, so that you can use it more ably, more capably. It's not good to use software when you don't know how it works. There's the problem of garbage in, garbage out. If you don't know, have some idea how the software works, you're probably not going to make as effective use of it. It's complicated. Quantum mechanics is complicated enough. You sort of need to read the manual. It's not like your iPhone where you can just kind of mess around until it does what you want. You can try that, and maybe you'll get lucky, but that's not usually the way research works. Anyway, so another reason why we want to know about these methods is because, of course, these methods continue to evolve, and so if we're going to continue to expand, evolve, improve these methods, then we're going to need to know how these methods work. And so we, first of all, we don't want to think of computational quantum chemistry software as something different from approximation methods. They're just these approximation methods that we're learning about here, essentially implemented in a computer. Another reason why we want to deal with the more basic, simpler approximation methods or models is that a lot of important chemical concepts that have been developed, that were developed several decades ago, but are still in wide use. A lot of these chemical intuition concepts really derive from these more basic methods. So, concepts such as, screening, steric effects, conjugation, these all derive from more basic approximation methods. So they give you qualitative answers, but sometimes qualitative answers are more satisfying. They give you more of a answer of why that you can't really get from just some table of numbers. Okay, so in order for that table of numbers to speak, you really need to look at these simpler models and more basic approximation methods. It's useful for developing various concepts that are widely in use. And then of course, once we know the theoretical underpinnings of these concepts, we can use them more capably. They're not just sort of an idea that's out there in the ether that just sort of, or that was, delivered by the experts. They're actually, real life concepts that we can examine, that we can look at the theoretical underpinnings and the assumptions involved, and we can evolve these concepts or apply them to new systems that perhaps the original developers of these concepts didn't have in mind. And so in order to have that, it's good to know, okay, where do these ideas come from? And so that's another reason why we want to look at these simple approximation methods. It's not just because we like big equations or that sort of thing. The other thing is, there's often a trade-off, and I've kind of alluded to this before. There's often a trade-off between accuracy and simplicity. You can have a very accurate table of numbers, but it won't tell a simple story. It won't tell you necessarily give you a clear idea about the relationship between the system parameters, the the structure of the molecule, the atoms involved, and so on. Temperature, whatever, dipole moment. It won't give you necessarily a clear relationship between these underlying system parameters and the predicted characteristics or outcomes for your system. So a simpler model often makes these relationships clearer. There's going to be fewer parameters, simpler functions, graphs that are easier to interpret relative to the sort of brute force, very accurate method that doesn't really tell you how it got there. Okay, so that brings us to, so that was just a little bit of introduction to some of the issues related to approximation methods. So approximation methods, they can often get you arbitrarily close to the answer that you, the true answer, or they can be simple models that show clear relationships between variables, but maybe don't give you, 4 significant figures of accuracy. And depending on the questions that you're asking, you sort of want, you sort of need both. It's not that one is superior to the other. Okay, so let's move on to this variational method. So our problem is that we have a system where we know the Hamiltonian, but we don't know psi. And so we can't solve the Schrodinger equation, h psi equals E psi. We can't find psi directly, and there's a lot of indication that there really is no simple functional form that will give you what psi is, what the wave function is. And if we don't know the wave function, we can't know the energy. Okay, so we have to settle for approximations. But again, approximation doesn't mean we'll never know the answer. We can get the answer to whatever degree of accuracy that we need, with some limitations due to, say, computer hardware, how long you're willing to wait, that sort of thing, storage space on the computer. That's it for simple systems with a few atoms to maybe a couple of dozen atoms. You can get answers that are essentially exact. Using approximation methods. Okay, so let's talk about the variational method. So we can't solve this Schrodinger equation exactly directly, the usual way that one might solve, get an analytical solution to a differential equation. So we have to use approximation methods to solve our differential equation. And of course, there are a lot of approximate methods to solving differential equations. There are some that are specifically useful for quantum mechanics, and that's where this variational approach comes in. And the idea is we come up with a parameterized approximate wave function. It's going to have typically at least 3 coordinates, often more coordinates, because you have to have coordinates for all of the particles involved. So it's going to be some function of, say, x, y, and z, or x1, y1, z1, x2, y2, z2 for the second particle or second electron, and so on. And then there's going to be a series of parameters, c1, c2, c3, and these are adjustable parameters. Okay, and so we can adjust the shape of our wave function to match, to get pretty close to the shape of the true but unknown wave function. We can adjust the parameters to try to get as close to that as we can, and we'll talk about the scheme for that momentarily. So what do I mean by a parameterized function? Here's some just quick examples. I'm not going to spend a lot of time talking about them, each one individually, but you can imagine a polynomial, something like a Taylor series expansion, where you have different polynomial coefficients, and you can adjust those polynomial coefficients to match pretty much any shape curve that you want. And so you can look at it as kind of a fitting problem, although yeah, how that works we'll talk about more materially. Another way we can look at it is superposition, where we have wave function solutions to a simpler Hamiltonian or a product of them in the case, to get you enough coordinates. And then your approximate wave function can be a sum of those product wave functions, where you have, again, different linear coefficients, C sub I. And of course, you can pick how many parameters you want based on the accuracy that you need and the resources at hand. And another approach is you can think of it as like sines and cosines or complex exponentials with different linear coefficients associated with each of those waves. So this is kind of a Fourier transform approach where we essentially would be using different Fourier coefficients to represent our wave function. And so I'm being a little flip here in saying, well, there's all these different ways we can approximate our wave function. We really actually, in most cases, want to carefully choose our functional form, whether that's superposition. That approach is used. The Taylor series type expansion usually is not used, in my experience, at least. I haven't seen much of that in my looking through the relevant literature. But you do see sometimes plane waves, and you see a superposition type approach, and you see other kinds of parameterized functions where there's just different parameters that affect the shape of your, say, exponential function or things like that. But we should carefully choose, because if we choose well, then we can approximate our wave function with very few linear coefficients. And so that would make the calculations more accurate given fewer terms, and in other words, it'd be more efficient. And also, if we're going to actually solve the problem not using a computer but using pen and paper, we definitely want to keep the number of terms to a minimum, and in fact we will perform variational calculations with as few as just one parameter. Okay, so let's but on a computer, of course, you're free to use lots and lots of parameters, as we'll see. So let's talk about this variational theorem. The variational theorem is we have some kind of trial, we call it a trial wave function, our approximate wave function, we call it trial, psi trial. And again, it's a function of all of our coordinates. Again, I've only said x, y, and z, but there may be multiple particles, so it could have x1, it could have multiple particles, each with its own set of x, y, and z coordinates. And then there's one or more parameters. And we can't use h psi equals e psi, so we do something close. We can't solve h psi equals e psi, but we can calculate the expectation value of the Hamiltonian. So that would be the expectation value of the Hamiltonian for this trial wave function. And that's going to give us an expectation value of the energy, right? The Hamiltonian gives us energy. Okay, so this works even if psi is not an eigenfunction in the Hamiltonian. Right? We can take any function, any operator, as long as they have the same set of coordinates, and we can calculate an expectation value. So far so good, right? We haven't run up against any brick walls. So here's where the theorem comes in. Okay, so we've defined our, or we have this expectation value for our Hamiltonian. It's our real Hamiltonian. The Hamiltonian doesn't have approximations in it, but the wave function is approximate. The Hamiltonian will have all of the physics, electron-electron repulsion, all that stuff will be in there, or as much as you want. The trial function, has perhaps that's usually where most of the approximations come in. And again, it's this parameterized function. Okay, so the variational theorem is that this expectation value, this integral here, is always greater than or equal to the ground state energy. Okay, so that's important because, okay, so this is saying the expectation value for our energy, which is given by this expectation value of our Hamiltonian for the trial wave function, that has to be greater than or equal to the true ground state energy for the system. Therefore, this turns our parameter hunt into a minimization or optimization problem. And of course, engineers are often pretty familiar with minimization or optimization problems. Basically, you're trying to find the set of parameters that optimizes a process, say for efficiency, cost, that sort of thing. And another way to look at it is minimization, optimization problems are also involved in curve fitting, where you have a set of data points and you have some trial curve, and you adjust the parameters in that curve to try to best fit your wave function, and thus you might extract some information about the data. For instance, the data could represent, a kinetics decay, and you could be fitting to an exponential first order decay or a second order or whatever order it is, and then you get out of it. What do you get out? You get out a fit value for the decay rate constant. So in this case, we're going to be getting kind of like a fit value for these parameters. Okay, so first of all, let's define something called the variational energy. And again, I didn't define it above, but we'll define it here. Our variational energy is given by this integral of our trial wave function, sandwiching our real Hamiltonian that has, again, there's really no penalty for putting in all of the physics there, but we have our simplified, trial wave function, and we're calculating an expectation value. Now, this trial wave function may not be normalized, so we have to be careful. And this little thing in the denominator here, this forces normalization. It's basically instead of sorry, press the wrong button there somewhere. Okay. So instead of having a kind of a two-step process where we, first define our wave function and then normalize it and then take an integral, we're just going to kind of combine those steps. And now if we know that our wave function is designed in such a way that it's always normalized regardless of the value of the parameters, then we don't need to divide, to put that integral in the denominator, that normalization integral. Okay, so that's going to give us, so when we perform that integral, we end up with a function of one or more variables, and those variables are the parameters. So we end up with this multi-dimensional energy surface, and we want to find what the minimum is on this surface. And again, you may recall from calculus or other places where minimization shows up, the minimum or the maximum is going to occur where the slope is 0. However, if we have a multi-dimensional function like we might have in this case, we actually end up with multiple simultaneous equations. So what we do is we have to do this here, take the partial derivative of our variational energy with respect to each of the parameters. So if we have a fairly simple trial function, we may end up with a simple function of these parameters, some kind of polynomial in the various c sub i's. And we can take a derivative of that and set it equal to 0. That's going to tell us, set it equal to 0, and then solve for the various c sub I. So we end up with a set of simultaneous equations. Say in the case of 2 parameters, we're going to have variational energy with respect to derivative with respect to C1, set that equals 0, and then we have a second equation, partial derivative of the variational energy with respect to C2, set that equals 0, so that gives us 2 equations. So again, let's assume maybe that these functions are some polynomial in C, in C1 and C2, and we can just take these derivatives, set them equal to 0, we get 2 equations, 2 unknowns, and we can solve that, right? So we solve the resulting simultaneous equations. That's going to give us back our parameters. Now then, we're not quite finished yet. We still have to then plug those parameters back into the variational energy. That's going to give us the energy at the minimum. And then also, of course, we can plot the resulting trial wave function or look at its characteristics, and that wave function will be a function of those parameters that we've just obtained. Okay, so that was just basically a quick overview of approximation methods. We're going to skip, again, perturbation methods for now. We're going to bring them up as it gets closer to time where we actually use them. And instead, we're going to move straight on to our first example of using these approximation methods, and that will be for the helium atom and for other multi-electron atoms. So that's the next lecture. See you then.